So today's topic is dienes from modern organic chemistry. Dienes introductions. The alkadienes, or as they are more commonly known as the dienes, are unsaturated hydrocarbons containing two carbon-carbon double bond per molecules. They have the general formula CnH2n-2 and isomeric with alkynes, but the behavior of dienes and alkynes is quite different from each other. Dienes are divided into three classes depending upon the arrangement of double bonds in the molecules. The three classes are isolated dienes, the dienes in which double bonds are separated by more than one single bond are called isolated dienes. For example, 1,4-pentadiene, 1,5-hexadiene. Cumulated dienes, the dienes in which the two double bonds are present between successive carbon atoms are called cumulated dienes or allenes or cumulines. For example, 1,2-propadiene or allene and 1,2-butadiene or methylalene. Conjugated dienes, the dienes in which the double bonds are separated by a single bond are termed as conjugated dienes. For example, 1,3-butadiene, 2,4-hexadiene. Nomenclature. Cumulated dienes are commonly named as alkyl derivative of allene, which is the simplest member of this type of dienes. For example, methylalene, 1-ethyl 3-methylallene, 1,1-dimethylalene. IUPAC nomenclature of all type of dienes is similar to that of alkene, except that the numeral di is added before the suffix "-ine" to indicate the presence of two double bonds. For example, 1,2-propadiene, 1,2-butadiene, 1,3-butadiene, 5-methyl 1,3-hexadiene, 1,5-heptadiene, 2,7-dimethyl 2,5-octadiene. Relative stabilities of dienes. It is interesting to note the difference in the relative locations of double bonds in the molecules causes appreciable difference in the relative stabilities of different classes of dienes. The data on heat of hydrogenation of alkenes and dienes clearly shows that conjugated dienes are more stable than the non-conjugated dienes. For a diene, the total heat of hydrogen may be expected to be the sum of the heat of hydrogenation of individual double bonds. This is found to be so for non-conjugated dienes. For instance, the observed heat of hydrogenation of 1,4-pentadiene is 254.4 kJ mole inverse, while the expected value is 251 kJ mole inverse. But in case of conjugated dienes, the observed values are lesser than the anticipated values. For example, the actual heat of hydrogenation of 1,3-butadiene is 238.2 kJ more inverse, which is 12.8 kJ lesser than the expected value. Similarly, the heat of hydrogenation of 1,3-pentadiene is about 16.7 kJ lesser than the expected value. Now, two isomeric dienes which differs only in the relative location of double bonds, example 1,4-pentadiene and 1,3-pentadiene, give rise to the same alkene on hydrogenation. Still, if the conjugated dienes evolves lesser energy than the non-conjugated one, only mean that the former contains lesser energy than the latter. In other words, conjugated diene system is more stable than the non-conjugated diene system. The greater stability of conjugated dienes may be explained in terms of resonance or delocalization. Structure of 1,3-butadiene. It has been stated above that conjugated dienes are more stable than non-conjugated dienes. The extra stability of conjugated dienes can be explained in terms of their structure as discussed below by considering the structure of 1,3-butadiene. Resonance structure. Unlike non-conjugated dienes, conjugated dienes exist as a resonance hybrid of various contributing structures. For instance, 1,3-butadiene is a resonance hybrid receiving contributions from many structures, the more important of which are 1, 2, and 3, where 1 is CH2 double bond CH single bond CH double bond CH2, and double bond is CH2 with positive sign, single bond CH, double bond CH, single bond CH2 with lone pair. where structure 3 is CH2 with lone pair single bond, CH double bond CH single bond CH2 with positive sign. It should be noted that structure 2 and 3 involve separation of charged particle. As such, structure 1, which does not involve any separation of charge, is the most stable and therefore the most important of all the contributing structure. The actual structure of 1,3-butadiene is a resonance hybrid which lies somewhat in between the contributing structure but resembles the structure 1 more closely. This remains that the bond between 1 carbon and 2 carbon or 3 carbon and 4 carbon is not a pure double bond but quite close to it. Similarly, the bond between 2 carbon and 3 carbon is in between a single and double bond but nearer to a single bond. This is in keeping with the fact that double bond length between 1 carbon and 2 carbon or 3 carbon and 4 carbon is nearly the same as that of carbon double bond. While the bond length between 2 carbon and 3 carbon 148 picometer or 1.48 angstrom is somewhat lesser than that of a carbon single bond carbon. Thus the relative greater stability of butadiene can be attributed to resonance. The resonance energy being 14.6 kJ mole inverse, a similar situation is responsible for the greater stability of other conjugated dienes as well. Orbital structures. The orbital picture of conjugated dienes afford a better way of understanding the nature of bonds in conjugated dienes. For this purpose, let us again consider 1,3-butadiene as a typical case. Each of the 4 carbons of 1,3-butadiene use the 3 sp2 hybrid orbitals for the formation of sigma bonds and an unhybridized p orbital for the formation of pi bonds. Figure 3.1a shows p orbital of the 4 carbon atom of butadiene before the formation of pi bonds. Overlapping of p orbitals of 1 carbon with that of 2 carbon and of the p orbital of 3 carbon and 4 carbon as shown in figure 3.1b. However, if the 4 carbon and the hydrogens attached to them lie in the same place, then the p orbital of 1 carbon and 2 carbon can also overlap as depicted in figure 3.1c. This means that there is an overlapping of p orbitals of 1 carbon with 2 carbon and 2 carbon with 3 carbon and 3 carbon with 4 carbon as shown in figure 3.1d. This results in the formation of a pi molecular orbital which covers all the 4 carbon atoms figure 3.2e. As already explained, such a molecular orbital which is spread over the nuclei of more than 2 atoms is known as delocalized molecular orbital, and the electron present in it are termed as delocalized electrons. As in case of normal or localized molecular orbital, delocalized molecular orbital also consists of 2 electron clouds, one lying above the plane of atom and the other lying below it. The presence of delocalized orbital is supported by the fact that the bond carbon-carbon single bond length nor carbon-carbon double bond length. Figure 3.1. Thus, the greater stability of 1,3-butadiene is due to the presence of delocalized electron, as each pair of delocalized electron is attracted by 4 and not 2 nuclei. The same explanations also applies to other conjugated systems. More recently, it has been suggested that the greater stability of conjugating dienes is due to variations in bond length and bond energy due to a particular hybrid states of carbon atoms. Method of formation of dienes. Dienes are generally produced by suitable variations of the method employed for the preparation of simple alkenes. The more commonly employed methods are given below. Catalytic dehydrogenation of alkenes or alkanes. For example, 1,3-butadiene may be prepared by passing the vapors of N-butane over heated Cr2O3 या फिर Al2O3 catalyst. 1,3-butadiene is also obtained by passing the vapors of 1-butene or 2-butene over heated nickel phosphate or calcium phosphate. Dehydrogenation of dihalogen derivatives. For example, on heating with alcoholic potassium hydroxides, 1,3-dichloro-3-methylbutane gives isoprene. Dehydration of diols in the presence of acids. For example, dehydration of 1,4-butane diol by heating in the presence of sulfuric acid or phosphoric acids results in the formation of 1,3-butadiene. Pyrolysis of cycloalkanes, retrodieldar reactions. For example, 1,3-butadiene can be prepared by passing the vapors of cyclohexene over heated nichrome, an alloy of nickel, chromium, and iron. Chemical reactions of dienes. The chemical properties of dienes are essentially due to the presence of two carbon-carbon double bonds in their molecules. Thus, non-conjugated dienes behave in exactly the same manner as simple alkenes, except that the attacking reagent is consumed in twice the amount required for one double bond. In case of conjugated dienes, however, the properties of the double bond are considerably modified due to the characteristic relative arrangement of double bonds. This relative arrangement enables the two double bonds to interact with each other so as to modify the behavior of the molecule as a whole. Thus, conjugated dienes are characterized by their greater stability and the occurrence of 1,4 addition reactions. The important reactions of dienes are discussed below to illustrate their behavior. Electrophilic addition reactions 1, 2 and 1,4 addition reactions. Dienes undergoes the usual electrophilic addition reactions shown by alkenes. However, due to the presence of two double bonds in the molecules of dienes, the two quantity of addendum is naturally two times that required for an alkenes. The important electrophilic addition reactions are given below. Addition of halogens. When treated with halogens, diene react with 2 moles of halogens per mole of dienes to form tetrahalogen derivative. For example, 1,3-butadiene plus 2Br2 gives 1,2,3,4 tetrabromobutane. The really interesting point, however, is what happens when only 1 mole of the addendum is made to react with 1 mole of the diene. In such a case, the two double bonds in a non-conjugated diene act independently of each other and addition takes place across either of the double bonds. For example, 1,4-pentadiene gives with Br2 gives 4,5-dibromo 1-pentene, but a different situation prevails in case of conjugated dienes. To illustrate it, let us consider the addition of 1 mole of bromine to 1,3-butadiene. The product obtained consists of a mixture of 3,4-dibromo 1-butene to 1,4-dibromo 2-butene. The formation of 3,4-dibromo 1-butene is not surprising as it is the result of normal addition, also termed 1,2 addition to adjacent carbon atom linked by a double bond, but the formation of 1,4-dibromo 2-butene due to 1,4 addition, that is addition at terminal carbons of the conjugated system, appears to be unexpected. Mechanism of 1,2 and 1,4 addition to conjugated dienes. To understand the occurrence of 1,2 and 1,4 addition reactions, let us examine the mechanism of addition of bromine to 1,3-butadiene. The reaction takes place in two steps through the initial formation of allylic carbocation. Formation of carbocation. As the bromine molecules approaches the dienes and get polarized, the positively polarized bromine adds to C1 of butadiene to form allylic carbocation and a negative bromide ion. A primary carbocation CH2 double bond CH CH2 positive could also be formed by the initial addition of bromine to carbon 2, but the ions A is formed in preference to this primary carbocation, as the former is not only a secondary but also an allylic cation, which but also an allylic cation which is stabilized by resonance between structures A and B. The two contributing structure A and B differ from each other in the location of double bond and of the positive charge. In the resonance hybrid of these structures, the positive charge is not localized on carbon 2 or carbon 4 but is spread over the both as shown below. Addition of bromide ion. It is clear that there are two positive charge centers in the cation which may be attacked by negative bromide ion in the second step of addition. Addition of bromide ion at carbon 2 would give 1,2 addition product, while addition of bromide ion at carbon 4 would give 1,4 addition product. Addition of halogen acids. Addition of halogen acids to conjugated dienes is similar to the addition of halogens. Addition of 1 mole of halogen acid to a conjugated diene gives rise to both 1,2 and 1,4 addition products. Mechanism. To start the reaction, in butadiene molecules abstract hydrogen ions from hydrogen chloride to form an allylic carbocation and a negative chloride ion. Initial addition of hydrogen ion could also take place at carbon 2, giving a primary carbocation, but the ion C is formed in preference to this primary carbocation, as the former is not only a secondary but also an allylic cation which is stabilized by resonance between structures C and D. The resonance hybrid of these contributing structure may be represented as shown below. Thus, there are two positive centers which may be attacked by negative chloride ions in the second step of addition. Addition of chloride ion at carbon 2 would give 3 chloro 1 butene 1 to addition, while addition of carbon 4 would give 1 chloro 2 butene 1 for addition. Effect on temperature on 1 2 and 1 4 addition to conjugated dienes. It has been found that the ratio in which the 1 2 and 1 4 addition product are formed in a result of electrophilic addition to conjugated dienes is largely governed by temperature at which the reaction is carried out. Generally speaking, 1 2 addition product is formed preferentially at lower temperature and is non-polar solvents, while 1,4 addition product predominates at higher temperature and in polar solvents. For example, 1,3-butadienes at 193 Kelvin gives 1,2-adduct 80% and 300 Kelvin temperatures gives 1,2-adduct 20% plus 1,4-adduct 20% and 1,4-adduct 80%. Explanation of the effect of temperature on 1 2 and 1 4 additions. The effect of temperature on 1 2 and 1 4 addition reactions may be attributed to the following reasons. First, E activations led to a 1-2 addition product is less than that leading of 1-2 1-4 addition product. As such, 1-2 addition take place more readily than 1-4 addition. However, 1-4 adduct once formed is more stable than 1-2 adduct. Second, both the addition product can undergo ionization forming a common carbocation. This led to an equilibrium between the two products and the carbocations. It may be noted that the carbocation is the same as the intermediate carbocation formed during the first step of addition. Since the energy difference between 1,2 adduct and carbocation 1 is lesser than between 1,4 adduct and the carbocation, ionization of 1,2 adduct takes place readily while that of 1,4 adduct takes place slowly. At lower temperature, ionization of product occurs to a very small extent only so that the 1 2 adduct which is formed faster is the main product isolated. This means that at lower temperature the relative amounts of the two products obtained are in accordance with their relative rates of formation. In other words, the reaction is kinetically controlled. At higher temperature, ionization becomes more important. The 1 2 adduct, which is thermodynamically less stable, readily ionizes, while the 1 4 adduct, although formed slowly, does not ionize readily. As such, the 1 4 adduct is present in large quantity when the equilibrium is not ionized readily. As such, the 1 4 adduct is present in large quantity when the equilibrium is reached and therefore the main product obtained. In other words, at higher temperature, the reaction is thermodynamically controlled. Free radical addition reactions. Like simple alkenes, conjugated dienes also undergo certain free radical addition reactions in the presence of suitable organic peroxide. Moreover, addition of free radicals can again lead to the formation of both 1 2 and 1 4 addition products. For example, CH2 double bond CH single bond CH double bond CH2 plus BrCCl3 in presence of peroxide gives 1 2 addition product and 1 4 addition product. Mechanism. The mechanism of free radical addition such as that given above may be summarized as follows. Peroxide to radical. Radical plus BrCCl3 gives radical bond Br plus radical of CCl3. The resonance hybrid of E and F may be depicted as. It may be noted that the allyl free radical formed in step 3 is the resonance hybrid of structures E and F. In the resonance hybrid, the odd electron is distributed between carbon 2 and carbon 4. As a result, this allyl free radical can form either 1 2 or 1 4 addition product by abstracting a bromine atom from another molecule of BrCCl3. The newly formed CCl3 radical then carries on the chain process. It is interesting to note that the free radical addition to conjugated dienes proceeds at a much faster rate than similar reactions with simple alkenes. Even though conjugated dienes are themselves more stable than simple alkenes, this unexpected reactivity of conjugated dienes towards free radical addition is attributed to the much greater stability of the intermediate allyl free radical as compared with the intermediate free radical formed from simple alkenes. Therefore, the net E activation for the formation of an intermediate allyl free radical is lesser than E activations for the formation of intermediate free radical in case of simple alkenes. As such, the free radical addition to dienes take place more readily and at a faster rate. Diels-Alder reaction 4 plus 2 cycloaddition. This is one of the most important reaction of conjugated dienes. It involves an addition reaction between a conjugated diene and a compound containing a double bond called a dienophile, which means diene loving, to form a six-membered ring. Since the reaction involves the addition of a 4 pi electron system to a 2 pi electron system and leads to the formation of a cyclic product, it is often referred to as 2 4 plus 2 cycloaddition reactions. The product formed is often called as the Diels-Alder adduct. The simplest example of a Diels-Alder reaction is that between 1,3-butadiene and ethylene dienophile, but the reaction takes place very slow and in low yields. 1,3-butadiene plus ethylene at 473 kelvins gives cyclohexanes. The reaction takes place by a concerted single-step mechanism, during which carbon 1 and carbon 4 of the conjugated diene system get attached to the doubly bonded carbon of the dienophile. As a result, two new sigma bonds are formed at the cost of two pi bonds of the dienes and dienophile, as is clear from the above example. Diels-Alder reactions take place very readily when substituted alkenes containing electron withdrawing groups are used as dienophiles. For example, the reactions between 1,3-butadiene and acrolein dienophile takes place 373 Kelvin to form the adduct in quantitative yield. Maleic anhydride dienophile react regularly with 1,3-butadiene at room temperature to give quantitatively yield of the adduct. Factors which favors the reaction. It was originally stated by Elder that the reaction is favored by the following factors. Presence of electron withdrawing groups in the dienophiles. The favorable effect of electron withdrawing groups in the dienophile is very clear from the examples given below. It has been seen that acrolein, which contains a carbonyl group which is electron withdrawing, and maleic anhydrides, which has two carbonyl group adjacent to the carbon-carbon double bond, undergoes Diels-Alder reaction in quantitative yield even under mild conditions. Presence of electron releasing groups in the diene 2,3-dimethyl 1,3-butadienes affords an important example of a diene demonstrate the favorable effect of electron releasing groups in the dienes. This compound containing two methyl groups which are electron releasing is about 5 times more reactive in Diels-Alder reaction than 1,3-butadiene. For example, 2,3-methyl 1,3-butadiene more react with acrolein in quantitative yield at only 303 Kelvin, as against this 1,3-butadiene react with acrolein in quantitative yields only at 373 Kelvin. It has now been found that even if the location of the electron withdrawing and electron releasing groups in the dienophile and dienes are interchanged, the yield of the adduct remains unchanged. In other words, dienes having electron withdrawing groups would undergo the reaction readily with dienophiles having electron releasing groups. Stereochemistry of Diels-Alder reactions. The Diels-Alder reaction is highly stereospecific. The important aspects of its stereochemistry are as follows. S-cis conformation of dienes. The diene undergoing the reaction must be in the S-cis conformation rather than S-trans conformation. This is because only the S-cis conformation allows the end of the conjugated system to reach the doubly bonded carbons of the dienophile. Note: 1,3-butadiene can have two possible planar conformation design as S-cis and S-trans as shown below. Strictly speaking, these do not represent the true cis and trans forms. This is because the S-cis and S-trans conformation can be interconverted by rotation around the single bond. That is why the prefix S is used before the notation cis and trans, which signifies that the isomerism is with respect to single bond. Occurrence of syn additions. The reaction takes place by syn addition of the diene to the dienophile, and the configuration of the dienophile is retained in adduct as illustrated below. 1,3-butadiene plus dimethyl maleate gives dimethyl cis 4 cyclohexane 1,2. Synthetic utility of Diels-Alder reactions. The synthetic utility of the reactions lies in the fact that it can be used in the preparation of many cyclic compounds which would be difficult to prepare by other means. A prominent feature of the reaction is that it is extremely easy to carry out. In most cases, the reaction is both about merely heating the reactants together with or without a solvent. Polymerization reaction. Conjugated dienes have a strong tendency to undergo free radical polymerization to form useful high molecular weight polymers. Polymerization of 1,3-butadiene peroxide induced polymerization of 1,3-butadienes gives rise to polybutadiene. The formation of a polybutadiene involves predominantly 1,4 free radical addition of butadiene units to each other so that the product obtained still contains a double bond for each butadiene unit. Second, polymerization of 2-methyl-1,3-butadiene. The free radical polymerization of 2-methyl-1,3-butadiene or isoprene gives polyisoprene which resembles natural rubber. Thank you.